Aldehydes and ketones are organic compounds that contain carbon-oxygen double bonds. That is, the carbonyl group as a functional group. They have the general molecular formula CnH2nO. Aldehydes and ketones closely resemble each other in most of their chemical properties. Hence, they are often collectively referred to as carbonyl compounds. However, aldehydes and ketones differ in the nature of the groups that are attached to the carbonyl group. In aldehydes, one of the two available valencies of the carbonyl group carbon is essentially satisfied by an H atom, and the other by a hydrogen atom, an alkyl group or an aryl group. Hence, the general formula for aldehydes is RC double bond OH. If R is H, then the corresponding aldehyde is formaldehyde. If R is the methyl group, then it is an acetaldehyde. And if R is the phenyl group, then it is a benzaldehyde. In ketones, the two valencies of the carbonyl group are satisfied by two alkyl or aryl groups, R and R', which may be the same or different. If R and R' both represent the same group, then the ketone is called a simple ketone. If R and R' are different, then the ketone is called a mixed ketone. The general formula for ketones is RC double bond OR'. For example, acetone represents a simple ketone where both R and R' are the same. That is, CH3. Benzophenone, where both R and R' are C6H5, also represents a simple ketone. On the other hand, acetophenone, where R is a methyl group and R' is a phenyl group, represents a mixed ketone. Due to this difference in the nature of the groups attached to the carbonyl group, in aldehydes and ketones, their reactivity is different. For example, aldehydes oxidize with ease as compared to ketones. Let us now look at the significance of these compounds. Aldehydes and ketones are well known for their fragrance and flavor. For example, the smell of acetaldehyde is reminiscent of apples. Also, vanillin from vanilla beans, salicylaldehyde from meadows sweet, and cinnamaldehyde from cinnamon have very pleasant fragrances. Aldehydes and ketones both find significance in several biochemical processes. For example, glucose, a polyhydroxyaldehyde, is the chief product in photosynthesis. Respiration, which takes place via the combustion of glucose, is associated with the liberation of energy. Thus, it is the ultimate source of energy in plants and animals. These compounds have considerable industrial significance. They are used as solvents and as starting material for the synthesis of several other products. For example, acetone and ethyl methyl ketone are common industrial solvents. Formaldehyde is used to prepare bakelite. Urea formaldehyde glues and other polymeric products. Acetaldehyde is chiefly used as starting material for the synthesis of acetic acid. Ethyl acetate, drugs, and polymers. Benzaldehyde is used in the perfume and dye industries. Certain compounds are used for preparing adhesives, paints, resins, plastics, fabrics, and so on. Like other organic compounds, aldehydes and ketones also have two systems of nomenclature. They are the common system and the IUPAC system. The common names of aldehydes are derived from the names of the corresponding carboxylic acids that they form on oxidation. They are named by replacing the IC acid of carboxylic acid by aldehyde. Thus, the aldehydes formaldehyde, acetaldehyde, and benzaldehyde are named after formic acid, acetic acid, and benzoic acid respectively. As you can see, they are named by replacing the suffix IC acid with aldehyde. The positions of the side chains or substituents in the carbon chain of aldehydes are indicated by the Greek letters alpha, beta, gamma, and delta. The carbon that is directly linked to the aldehyde group is alpha carbon. The next carbon is beta carbon, and so on. For example, the given compounds can be named alpha-hydroxybutylaldehyde and beta-bromobutyraldehyde respectively. In the IUPAC system, aldehydes are named by replacing the E of the corresponding alkane by Al. Hence, the IUPAC name for aldehydes is alkanal. For example, the IUPAC name for formaldehyde can be written by replacing the letter E of the corresponding alkane methane by Al. Hence, the IUPAC name for formaldehyde is methanal. Similarly, the IUPAC names for acetaldehyde, propionaldehyde, N-butyraldehyde, isobutyraldehyde, and valeraldehyde are ethanal, propanal, butanal, 2-methylpropanal, and pentanal respectively. The substituents in the aldehydes are prefixed in alphabetical order along with numerals indicating their positions in the carbon chains. Thus, the IUPAC name of the given compound can be written as 3-bromo-2-chloro-4-methyl-hexanal. In case of aldehydes, the longest carbon chain is numbered starting from the carbon of the aldehyde group. Thus, the given compound is named 2-ethyl-3-methyl-pentanal. It must be noted that the C2 of the IUPAC name corresponds to the alpha of the common name. For example, the compound shown here bears the IUPAC name of 2-methylpentanal, while its common name is alpha-methyl-valeraldehyde. Here is a list of some aldehydes with their common and IUPAC names. From the list, you can see that the IUPAC name for alpha-chloroacetaldehyde is 2-chloroethanal and for acrolein it is 𝙄𝙃𝙊𝙃. In the IUPAC system, when the aldehyde group is attached to the ring, the suffix carbaldehyde is added after the name of the cycloalkane. For example, in cyclohexanaldehyde, the aldehyde group is attached to a 6-member cyclohexane ring. Hence, its IUPAC name can be written by adding the suffix carbaldehyde to the cyclohexane. That is, cyclohexane carbonaldehyde. Similarly, the IUPAC name for benzaldehyde can be written as benzene carbaldehyde. Note that the common name benzaldehyde is also accepted by IUPAC. To indicate the substituent on the ring, the numbering of the ring starts from the carbon atom to which the aldehyde group is attached. For example, the IUPAC name for gamma-methyl cyclohexanaldehyde is 3-methyl cyclohexane carbaldehyde. Similarly, while writing the IUPAC name for orthohydroxybenzaldehyde or salicylaldehyde, the substituent hydroxyl group gets the second position as the numbering of the ring starts from the carbon atom attached to the aldehyde group. Thus, the IUPAC name for this molecule is 2-hydroxybenzene carbaldehyde. Now let's look at the common names and the IUPAC names of some compounds. The common name metachlorobenzaldehyde is written as 3-chlorobenzene carbaldehyde in the IUPAC system. Similarly, para-nitrobenzaldehyde is 4-nitrobenzene carbaldehyde. Phthalaldehyde is benzene 1,2-dicarbaldehyde. Vanillin is 4-hydroxy,3-methoxybenzene carbaldehyde. Crotonaldehyde is 2-butanal, and cinnamaldehyde is 3-phenyl-propyl-2-phenyl. Let us now turn our focus to the nomenclature of ketones. In the common system, ketones are named simply by adding the suffix ketone to the name of the two alkyl groups. In case of simple ketones, where both the alkyl groups are the same, the prefix di is used for the alkyl group. For example, the compound CH3 C-double-bond-O, CH3, is named dimethyl ketone or simply acetone, while C2H5 C-double-bond-O, C2H5 is named diethyl ketone. In case of mixed ketones, the two different alkyl groups R and R' are mentioned in alphabetical order. For example, the compound CH3 C-double-bond-OC2H5 is named ethyl-methyl ketone. Similarly, CH3 C-double-bond-OC3H7 is named methyl N-propyl ketone. The positions of substituents in ketones are indicated by the Greek letters alpha, alpha dash, and beta, beta dash, and so on, where alpha, alpha dash are given to the carbon atoms adjacent to the keto group. For example, in the given molecule, the substituents, 2 bromine atoms, are present on the alpha dash and beta carbons. Hence, it is named alpha dash beta dibromodiethyl ketone. Alkyl phenyl ketones are usually named by adding the acyl group as a prefix to phenone. For example, when CH3 C-double-bond-O is attached to benzene ring, it is named acetophenone. Similarly, the molecule C2H5, C double bond O, C6H5 is named propiophenone. The ketone in which a carbonyl group is attached to two benzene rings is named benzophenone. According to the 𝙈𝙆𝙋 system, ketones are named by replacing the E of the corresponding alkane with -one. The longest chain carrying the carbonyl group is considered the parent chain, and the numbering begins from the end nearer to the carbonyl group. The compound shown here is named 4-methyl-hexane-3,1. In certain polyfunctional compounds, if the carbonyl functional group of the ketone is present as a substituent, then it can be indicated by the prefix oxo, and a number is indicated to show its position in a molecule. The example here contains three functional groups: hydroxyl, aldehyde, and ketone. According to 𝙈𝙆𝙋 rules, as the order of preference while naming is aldehyde, ketone, and then hydroxy, the carbonyl functional group of the ketone and the hydroxyl group of the alcohol are treated as substituents. Hence, the 𝙈𝙆𝙋 name is 5-hydroxy-4-oxohexanal. As aldehydes and ketones contain the same carbonyl group, their properties and methods of preparation are quite similar. Methods for the preparation of aldehydes and ketones include oxidation of alcohols, dehydrogenation of alcohols, ozonolysis of alkenes, hydration of alkynes, reduction of acid chlorides, and reduction of nitriles. Let us learn about each one of these in detail. Let us begin our discussion with the preparation of carbonyl compounds from alcohols. You have already learned that primary and secondary alcohols yield aldehydes and ketones on oxidation. The process of oxidation of alcohols involves the loss of alpha hydrogen. That is, the hydrogen atom attached to the carbon bearing the OH group. In the presence of reagents such as pyridium chlorochromate, PCC, or acidified potassium dichromate, or acidified potassium permanganate. Now, since primary alcohols contain two alpha hydrogens, they can either lose one of them to form an aldehyde selectively in the presence of pyridium chlorochromate, PCC, or can lose both of them to form a carboxylic acid in the presence of acidified potassium permanganate. The conversion of a primary alcohol into an aldehyde is difficult because aldehydes are susceptible to further oxidation. One of the best reagents for the conversion of primary alcohols into aldehydes is PCC. Note that the oxidation of primary alcohol to carboxylic acids is usually accomplished by the use of acidified potassium permanganate. For example, ethanol on oxidation with PCC gives ethanal, but gives ethanoic acid in the presence of acidified potassium permanganate. On the other hand, a secondary alcohol loses its only one alpha hydrogen to form a ketone in the presence of acidified potassium dichromate. For example, isopropyl alcohol on oxidation in the presence of acidified potassium dichromate gives propanone or acetone. Another method of preparing carbonyl compounds from alcohols is by the dehydrogenation of alcohols. This method is suitable for the oxidation of volatile alcohols. It involves passing vapors of an alcohol over metal catalysts like silver or copper. Dehydrogenation of primary alcohols yields aldehydes, while that of secondary alcohols yields ketones. For example, when vapors of ethyl alcohol are passed over heated copper at 573 Kelvin, dehydrogenation takes place and ethanol is formed. However, isopropyl alcohol yields acetone on dehydrogenation. Carbonyl compounds can also be prepared from the ozonolysis of alkenes. Ozonolysis involves the cleavage of the double bond by the addition of ozone to give a cyclic product called ozonide, followed by hydrolysis in the presence of zinc dust. Depending upon the substitution pattern of alkenes, ozonolysis yields either aldehydes or ketones or both. For example, 2-butene yields 2 molecules of acetaldehyde on ozonolysis, while 2,3-dimethyl-but2-ene yields 2 molecules of acetone. A molecule such as 2-methyl-2-butene yields a mixture of acetaldehyde and acetone on ozonolysis. Hydration of alkynes is yet another method for the preparation of carbonyl compounds. This method involves the addition of water to alkynes in the presence of mercuric sulfate and sulfuric acid to form aldehydes or ketones as the final product. For example, acetylene on hydration gives unstable vinyl alcohol, which tautomerizes to form the acetaldehyde. All other alkynes yield ketones in similar manner. For example, propyne gives acetone on hydration. Carbonyl compounds can also be prepared by the reduction of acid chlorides. Aldehydes can be prepared by the reduction of acid chlorides with hydrogen in the presence of palladium on barium sulfate in quinoline. This reaction is called Rosenmund's reduction. Aliphatic and aromatic aldehydes can be prepared by this method. Note that ketones cannot be prepared by this method. For example, adding hydrogen to acetyl chloride in the presence of palladium on barium sulfate in quinoline yields acetaldehyde. Similarly, Rosenmund's reduction of benzoyl chloride gives benzaldehyde. Ketones, on the other hand, are prepared by the treatment of acid chlorides with dialkyl cadmium. Dialkyl cadmium can be prepared by the reaction of cadmium chloride with Grignard reagents. For example, the reaction of methyl magnesium bromide with cadmium chloride gives dimethyl cadmium. The treatment of dimethyl cadmium with propanoyl chloride gives ethyl methyl ketone. Aldehydes and ketones can both be prepared from nitriles. Let's see how. Aldehydes can be prepared by the reduction of nitriles to imines followed by hydrolysis. The reduction of a nitrile to the corresponding imine by stannous chloride in the presence of hydrochloric acid, followed by hydrolysis to yield the corresponding aldehyde, is known as the Stephan reaction. For example, ethane nitrile on reduction in the presence of SnCl2 and HCl gives ethynylamine. This on hydrolysis in the presence of an acid gives ethanol as the final product. Alternatively, selective reduction by diisobutyl aluminium hydride (DIBALH) 𝐴2 followed by hydrolysis also yield aldehydes. For example, ethane nitrile, on reduction in the presence of DIBALH followed by hydrolysis, yields ethanol. Similarly, DIBALH can also be used to reduce esters to aldehydes, as shown here. Ketones, on the other hand, can be prepared by treating a nitrile with the Grignard reagent followed by hydrolysis. For example, propiophenone can be prepared by treating propane nitrile with phenyl magnesium bromide in ether followed by hydrolysis. Let us now look at the preparation of aromatic aldehydes and ketones. Aromatic aldehydes can be prepared from benzene or aromatic acid chlorides or methylbenzene or from benzyl halides. Let us discuss each method. Aromatic aldehydes can be prepared by treating benzene or its derivatives with carbon monoxide and dry hydrogen chloride gas in the presence of anhydrous aluminium chloride or cuprous chloride. This reaction is known as the Gattermann-Koch reaction. For example, benzaldehyde can be prepared by treating benzene with a mixture of carbon monoxide and dry HCl gas in the presence of anhydrous ElCl3. As you have seen earlier, Rosenmann's reduction of benzoyl chloride with hydrogen in the presence of palladium on barium sulfate in quinoline also gives benzaldehyde. Benzaldehyde or substituted benzaldehyde can also be prepared by the oxidation of methylbenzene with chromyl chloride to a chromium complex followed by hydrolysis. This reaction is known as the Itard reaction. Benzaldehyde can also be made from toluene. When toluene or substituted toluene is treated with chromic oxide in acetic anhydride, benzylidene diacetate is formed. This, on hydrolysis in the presence of an acid, yields the corresponding benzaldehyde. The hydrolysis of benzyl halides also yields aromatic aldehydes. For example, the hydrolysis of benzyl chloride, which is obtained by the side chain halogenation of toluene, gives benzaldehyde. Remember that this is the commercial method for manufacturing benzaldehyde. Aromatic ketones are more conveniently prepared by the Friedel-Crafts acylation. Benzene reacts with acid chloride in the presence of anhydrous aluminium chloride to give the corresponding ketone. This reaction is known as the Friedel-Crafts acylation. For example, benzene reacts with acetyl chloride and benzoyl chloride in the presence of anhydrous aluminium chloride to give acetophenone and benzophenone respectively. The physical and chemical properties of aldehydes and ketones are determined by the structure of the carbonyl group. It is, therefore, very important to understand its structure. Like the carbon-carbon double bond in alkenes, the carbon-oxygen double bond of the carbonyl group is composed of one sigma bond and one pi bond. The carbon atom in the carbonyl group undergoes sp2 hybridization in its excited state, leaving 1 out of 3 p orbitals unhybridized. The carbon to oxygen sigma bond is produced by the overlap of one sp2 orbital of carbon with a p orbital of oxygen. On the other hand, the carbon-to-oxygen pi bond is formed by the sideways overlap of the p orbitals of carbon and oxygen. The remaining two sp2 orbitals of carbon form 2 sigma bonds with the s orbital of hydrogen, as in formaldehyde, or 1 sigma bond with the s orbital of hydrogen and another sigma bond with an sp3 orbital of the carbon of the alkyl group, like in other aldehydes, or 2 sigma bonds with 2 sp3 orbitals of the carbon of the alkyl group, as in ketones. Thus, the carbonyl carbon and the 3 atoms attached to it lie in the same plane with a trigonal coplanar structure and a bond angle of 120 degrees, while the pi electron cloud lies perpendicular above and below the plane. It is important to note that the carbon-oxygen double bond in the carbonyl group is different from the carbon-carbon double bond in alkanes. In case of alkanes, the pi electron cloud is equally shared by 2 atoms, whereas in the carbonyl group, the pi electron cloud is attracted more towards the oxygen atom due to its greater electronegativity. Consequently, in the carbonyl group, the oxygen atom acquires a partial negative charge, while the carbon atom acquires a partial positive charge, thus making the carbonyl a polar group with a dipole moment value of 2.3 to 2.8 dBi units. However, the high value of the dipole moment can be accounted for both the inductive effect and the resonance effect. Now, let us look at the physical properties of carbonyl compounds. At room temperature, formaldehyde is a gas and acetaldehyde is a volatile liquid. Other aldehydes and ketones are liquids or solids at room temperature. Aldehydes and ketones have higher boiling points than hydrocarbons and ethers of comparable molecular weights. This is due to the weak intermolecular dipole-dipole interactions. Observe this table about compounds of almost similar molecular weights, 72 to 74. We see that non-polar hydrocarbons, like N-pentane and weakly polar diethyl ether, have lower boiling points than that of polar N-butyraldehyde and ethyl-methyl ketone. However, their boiling points are lower than that of N-butyl alcohol and propionic acid. This is because carbonyl compounds are not capable of forming intermolecular hydrogen bonding by themselves, since they contain a hydrogen bonded to carbon, but not to oxygen. Aldehydes and ketones are soluble in the usual organic solvents like benzene, ether, and chloroform. To know their solubility in water, refer to this table, which shows the solubility of a compound in grams per 100 grams of water. We see that the lower aldehydes and ketones, such as formaldehyde, acetaldehyde, and acetone, because of their ability to form hydrogen bonding with water, are miscible in water in all proportions. Notice that solubility decreases with an increase in the length of the carbon chain. The lower aldehydes and ketones have a characteristic pungent odor. with an increase in the size of the molecule, the odor becomes less pungent and more fragrant. Therefore, many naturally occurring aldehydes, such as vanillin from vanilla beans and cinnamaldehyde from cinnamon, and ketones such as acetophenone, are used to blend perfumes and as a flavoring agent. As both aldehydes and ketones contain the carbonyl group, they resemble each other closely in most of their properties. The carbonyl group governs the chemistry of aldehydes and ketones in two ways: by providing a site for nucleophilic addition and by increasing the acidity of the hydrogen atoms attached to the alpha carbon. Both of these effects are due to the ability of oxygen to accommodate the negative charge. The typical reactions of aldehydes and ketones are nucleophilic addition reactions. Before we examine the different types of nucleophilic addition reactions, let us first understand the general mechanism of nucleophilic addition reactions. The first step is a slow or the rate-determining step, which involves the attack of a nucleophile on the electron-deficient carbonyl carbon. Since the carbonyl group is flat, it is liable to be attacked from above or below the planar carbon atom. As the nucleophile forms a bond with the sp2 planar carbonyl carbon atom, the electron pair of the carbon to oxygen pi bond shifts to the carbonyl oxygen. The carbonyl oxygen easily accommodates the electron pair to produce a tetrahedral sp3 alkoxide ion intermediate. In the second step, the alkoxide ion captures a proton from the reaction medium to give an electrically neutral tetrahedral product. If the nucleophile is strong, it will readily attack the carbonyl carbon. The resulting addition product can be readily protonated by the solvent or by the added acid. However, if the nucleophile is weak, then it requires an acid catalyst to make the nucleophilic addition reaction occur at a reasonable rate. The acid protonates the carbonyl oxygen to produce an oxonium ion. The oxonium ion is highly reactive towards nucleophilic attack at the carbonyl carbon atom. This is because the carbonyl carbon atom carries more positive charge than it does in the unprotonated compound. The addition of alcohol to the carbonyl group is an example of acid-catalyzed nucleophilic addition. The reactivity of the carbonyl group towards nucleophilic addition depends mainly upon the magnitude of the positive charge on the carbonyl carbon. That is, the electronic factor and the extent of crowding around the carbonyl carbon atom in the transition state. That is, the steric factor. Based on these factors, the order of reactivity is formaldehyde without any alkyl group is more reactive than other aldehydes with one alkyl group, which, in turn, are more reactive than ketones that contain two alkyl groups. Electronically, alkyl groups are electron-releasing groups that release electrons and stabilize the carbonyl carbon by reducing the magnitude of positive charge on it. Hence, the electrophilicity on the carbonyl carbon, and therefore the reactivity, decreases with an increase in the number of alkyl groups. Sterically, the presence of bulkier alkyl groups in ketones hinders the approach of the nucleophile towards the carbonyl carbon. Hence, the bulkier the alkyl group, the lesser is the reactivity. Therefore, the decreasing order of the reactivity of ketones is acetone is more reactive than 𝙁𝙆𝙋𝙀𝙀, which is more reactive than isopropyl-methyl-ketone, methyl-tertiary-butyl-ketone. An aryl group has an electron withdrawing inductive effect, so it is expected to destabilize the reactant and speed up the reaction. However, it seems to stabilize the reactant even more by resonance, and thus decreases the reactivity. Thus, propanal is more reactive than benzaldehyde because the polarity of the carbonyl group is reduced in benzaldehyde as shown. Now let us look at some important examples of nucleophilic addition on the carbonyl group. These include addition of hydrogen cyanide, addition of sodium bisulfite, addition of Grignard reagent, addition of alcohols, addition of ammonia and its derivatives. When hydrogen cyanide is added to the carbonyl group of aldehydes and ketones, it yields compounds known as cyanohydrins. As HCN is a very weak acid, it is a poor source of cyanide ions. Hence, addition takes place very slowly. Therefore, the addition of a base can generate cyanide ions from the weak acid, HCN, causing a dramatic increase in the rate of the reaction. The cyanide ions, being stronger nucleophiles, rapidly attack the carbonyl carbon to produce the corresponding cyanohydrins. Cyanohydrins are useful intermediates in organic synthesis. They undergo hydrolysis to yield alpha-hydroxy acids or unsaturated acids. For example, the addition of HCN to acetaldehyde yields acetaldehyde cyanohydrin, which, on hydrolysis, yields lactic acid or alpha-hydroxypropanoic acid. Let's look at the addition of sodium bisulfite. When sodium bisulfite is added to an aldehyde or a ketone in the presence of ethanol, it gives a water-soluble solid adduct. This solid adduct is filtered from ethanolic solution and then decomposed by an acid or a base to regenerate the carbonyl compound. Hence, this reaction is used for the purification and separation of carbonyl compounds. For example, acetaldehyde reacts with a saturated solution of sodium bisulfite to give a white crystalline precipitate of acetaldehyde sodium bisulfite. Yet another addition reaction is the addition of a Grignard reagent to the carbonyl group. In this addition reaction, when a Grignard reagent, RMgX, is added to the carbonyl group, with its organic group R being attached to the carbonyl carbon and magnesium to the carbonyl oxygen, it produces an addition compound, which on hydrolysis yields an alcohol. As you can see, formaldehyde produces a primary alcohol, a secondary alcohol with the other aldehydes, and tertiary alcohols with ketones. This relationship arises directly from our definitions of aldehydes and ketones, and our definitions of primary, secondary, and tertiary alcohols. Aldehyde reacts with alcohol in the presence of anhydrous hydrogen chloride to form an unstable intermediate known as hemiacetal. Hemiacetal further reacts with one more molecule of alcohol to give a 𝙤𝙈𝙋𝙍 compound known as acetal. This reaction is an example of acid-catalyzed nucleophilic addition in which 𝙤𝙈 gas protonates the oxygen of the carbonyl group so that the oxonium cation formed is more susceptible to nucleophilic attacks. All steps involved in the formation of acetals from an aldehyde are reversible. Ketones react with an excess of ethylene glycol under similar conditions to form cyclic products known as ethylene glycol ketones. Both acetals and ketones can be rapidly hydrolyzed with aqueous mineral acids even at room temperature into aldehydes and ketones respectively. Let's now look at the addition of ammonia and its derivatives. When nucleophiles such as ammonia and its derivatives NH2G are added to the carbonyl group in the presence of acid, they form compounds with carbon to nitrogen double bonds known as imines. Let's understand the mechanism of this reaction. 1. Initially, the hydrogen ion from the acid attaches itself to the carbonyl oxygen to produce an oxonium cation. 2. This is followed by a nucleophilic attack by the basic nitrogen on the carbonyl carbon to form an intermediate addition product. 3. Further, the elimination of the water molecule from the intermediate results in the formation of the product with the carbon to nitrogen double bond. Since these reactions involve the addition of a nucleophile in the presence of an acid followed by the elimination of the water molecule, they are termed as nucleophilic addition-elimination reactions. Aldehydes and ketones react with ammonia derivatives with the general formula NH2G. Here, G is equal to R, alkyl group, OH, NH2, NH, C6H5, NH, CO, NH2, etc. Aldehydes and ketones react with primary amines to form substituted imines, a Schiff's base. Aldehydes and ketones react with hydroxylamine to form the corresponding oximes. For example, acetaldehyde and acetone react with hydroxylamine to form acetaldoxime and acetoxime respectively. Aldehydes and ketones react with hydrazine, NH2NH2, and its derivatives such as phenylhydrazine, 2,4-dinitrophenylhydrazine and semicarbazine to form the corresponding hydrazones. For example, acetaldehyde and acetone react with hydrazine to form acetaldehyde hydrazone and acetone hydrazone respectively. Similarly, they react with hydrazine derivatives and form the corresponding hydrazones as shown in the equations here. Hydrazones are usually insoluble solids with sharp melting points. Moreover, oximes and hydrazones, when refluxed with dilute hydrochloric acid, regenerate the parent aldehyde and ketone. Hence, oximes and hydrazone are used for the detection and purification of organic compounds that contain the carboxylic functional group COOH are called carboxylic acids. The name carboxyl is derived from the carbonyl group C double bond O and the hydroxyl group OH of which it is composed. Carboxylic acids are widespread in nature. Higher members of aliphatic carboxylic acids, known as fatty acids, are important components of the biomolecules such as lipids, fats and oils. Aliphatic carboxylic acids have been known for a long time. A large number of them are known by their common names that refer to their sources rather than to their chemical structures. The common names for carboxylic acids are usually derived from Latin or Greek words that indicate the original source of the individual acid. All common names of these acids end with IC acid. For example, the name formic acid, HCOOH, is derived from the Latin word formica, which means red ants, while acetic acid, CH3COOH, is derived from the Latin word acetum, which means vinegar. Similarly, butyric acid is derived from the Latin word butyrum, which means butter. The name caproic acid, which is obtained from goat fat, is derived from the Latin word capra, which means goat. A dicarboxylic acid contains two carboxyl groups. The table here gives the common names of some dicarboxylic acids. Their names can be easily remembered by the mnemonic 𝙁𝙆𝙋𝙊𝙍𝙍. When it comes to substituted acids, the position of the substituent is indicated by the Greek letters alpha, beta, gamma, etc. The carbon adjacent to the carboxylic is assigned the letter alpha, the next carbon beta, the next one gamma, and so on. For example, two methyl groups substituted on the alpha and beta carbons in a 6-carbon carboxylic acid is named alpha-beta dimethylcaprioic acid. Aromatic acids are named as the derivatives of benzoic acid, C6H5COOH. For example, compounds A and B shown here are named para-bromobenzoic acid and ortho-para-dinitrobenzoic acid respectively. Methylbenzoic acids are given the special names of toluic acids. For example, the compound shown here is named metatoluic acid. Now, let's look at the IUPAC system. In the IUPAC system, carboxylic acids are named by replacing the ending E of the corresponding alkane by OIC acid to form alkanoic acid. For example, the IUPAC name for carboxylic acid containing one carbon is methanoic acid, obtained by replacing the ending E of methane by OIC acid. Similarly, carboxylic acids containing 2, 3, and 4 carbon atoms are named ethanoic acid, propanoic acid, and butanoic acid respectively by replacing the ending E of the alkanes concerned by OIC acid. For naming the higher numbers, the longest chain containing the carboxyl group is selected, and numbering is done from the side of the carboxyl group, always giving it the number 1. For example, The compound shown here is named 4-methyl-hexanoic acid. For naming compounds containing more than one carboxyl group, the ending E of the alkane is retained, and the multiplicative prefix di, tri, etc. is added to the term oic acid. The position of the COOH groups are indicated by Arabic numeral before the multiplicative prefix. For example, the compound shown here, which contains 3 carboxyl groups on the first, second and third carbons, is named propane 1,2,3 tricarboxylic acid. In the 𝙈𝙆 system, benzoic acid is named benzene carboxylic acid. Note here that the common name benzoic acid is also accepted as the 𝙈𝙆 name. If side chains or substituents are present, then they are indicated by numbers, with the carboxyl carbon atom being numbered 1. For example, phenyl acetic acid shown here is named 2-phenyl-ethanoic acid. Similarly, phthalic acid is named benzene 1,2-dicarboxylic acid. The name of a salt of carboxylic acid consists of the name of the cation followed by the name of the acid, with the ending IC acid being changed to 8. For example, the compounds given here are named ammonium formate and potassium 2,3-dibromopropionate, respectively. Carboxylic acids can be prepared by several different methods: oxidation of primary alcohols and carbonyl compounds, oxidation of alkyl benzenes, carbonation of Grignard reagents, hydrolysis of nitriles, hydrolysis of acyl chlorides and anhydrides, hydrolysis of esters. Let us see how carboxylic acids can be prepared from primary alcohols and carbonyl compounds. Primary alcohols or aldehydes, on oxidation with oxidizing agents such as acidified or alkaline potassium permanganate, acidified potassium dichromate or chromium trioxide in sulfuric acid, gives carboxylic acids with the same number of carbon atoms. For example, 2-methyl-butane-1-ol on oxidation with acidified or alkaline potassium permanganate gives 2-methyl-butanoic acid. Aldehydes can also be oxidized to the corresponding carboxylic acids, even with mild oxidizing agents such as Tollens reagent or Fellings reagent. For example, acetaldehyde is oxidized to acetic acid in the presence of Tollens or Fellings reagent. Ketones also give carboxylic acids on oxidation. However, ketones are oxidized only under vigorous conditions, such as strong oxidizing agents and elevated temperatures. Under these conditions, ketones form a mixture of carboxylic acids with a fewer number of carbon atoms, as shown here. For example, butanone, on oxidation with hot concentrated nitric acid, gives a mixture of propanoic acid and methanoic acid. One of the most useful methods of preparing an aromatic carboxylic acid is the oxidation of an alkyl benzene. Chromic acid or acidic or alkaline potassium permanganate is generally used for this purpose. It must be noted that irrespective of the length of the side chain, the alkyl group is entirely oxidized into a carboxyl group. For example, toluene or ethylbenzene on oxidation with acidic potassium permanganate gives benzoic acid. It is important to note that only primary and secondary alkyl groups are oxidized into a COOH group, while tertiary alkyl groups remain unaffected. For example, N-propylbenzene and isopropylbenzene are oxidized to benzoic acid in the presence of chromic acid or acidic or alkaline potassium permanganate, while tertiary butylbenzene undergoes no change under these conditions. In the presence of these oxidizing agents, even suitably substituted alkenes are oxidized to carboxylic acids. For example, but2-ene on oxidation in the presence of acidified potassium permanganate gives ethanoic acid. Cycloalkenes, on the other hand, are oxidized to dioic acids under these conditions. For example, cyclohexene, on heating with acidified potassium permanganate, undergoes oxidation to adipic acid or hexane 1,6-dioic acid. The carbonation of Grignard reagents is another important method for the preparation of carboxylic acids. Grignard reagents react with carbon dioxide to form the magnesium salts of carboxylic acids. The free acid can be obtained from the salt by treating it with mineral acids. Grignard reagents can be obtained by the reaction of alkyl halides with magnesium metal in dry ether. The conversion of trimethyl acetic acid from tertiary butyl chloride is illustrated here. Did you notice that the acid formed by this method contains one more carbon atom than the alkyl halide? Thus, this method has the special advantage of increasing the length of a carbon chain. Hydrolysis of nitriles is another method for preparing the carboxylic acids. Nitriles, on boiling with aqueous alkali or acid, get hydrolyzed to the respective carboxylic acids. Aliphatic nitriles can be prepared by treating an alkyl halide with sodium cyanide in the presence of the solvent dimethyl sulfoxide. The synthesis of pentanoic acid from N-butyl bromide shown here illustrates the complete method. Note that the acids produced from the alkyl halide also contain one carbon atom more than the original alkyl halide. The hydrolysis of acid derivatives such as amides, acid chlorides, anhydrides, and esters yields carboxylic acids. Amides undergo hydrolysis on being boiled with a dilute acid or alkali. The hydrolysis yields carboxylic acid and an ammonium salt with an acid, and carboxylic acid and ammonia with an alkali. For example, acetamide, on being boiled with dilute HCl, undergoes hydrolysis to give acetic acid and ammonium chloride. On the other hand, when it is boiled with aqueous sodium hydroxide, it gives sodium acetate and ammonia. Acid chlorides, on hydrolysis, give carboxylic acids. For example, acetyl chloride on hydrolysis in presence of water gives acetic acid and hydrochloric acid. The hydrolysis of acid chlorides occurs readily in presence of an alkali. Hydrolysis in the presence of an alkali first yields carboxylate ions, which on acidification give the corresponding carboxylic acids. For example, when acetyl chloride is hydrolyzed with an alkali, it first yields acetate ions, which give acetic acid on acidification. Anhydrides give the corresponding acids on hydrolysis. For example, acetic anhydride gives acetic acid. Acid hydrolysis of esters directly gives the carboxylic acids concerned. For example, ethyl acetate, on boiling with a dilute acid, gives acetic acid and ethyl alcohol. Alkaline hydrolysis of esters, on the other hand, first results in the formation of carboxylates, which on acidification gives the corresponding carboxylic acid. For example, on boiling with aqueous sodium hydroxide, ethyl benzoate gives sodium benzoate and ethyl alcohol. Acidification of sodium benzoate gives benzoic acid. Having learned the different methods of preparation of carboxylic acids, now try to accomplish the following transformations. Benzyl chloride into phenyl acetic acid. Orthobromotoluene into orthobromobenzoic acid. Tertiary pentyl chloride into ethyl dimethyl acetic acid. The conversion of benzyl chloride into phenyl acetic acid involves an increase of one carbon atom. The conversion can be achieved by first treating benzyl chloride with sodium cyanide to yield phenyl acetonitrile, followed by hydrolysis with aqueous acid. This is a simple reaction of oxidation of the alkyl group. This can be achieved by the oxidation of orthobromotoluene in the presence of alkaline potassium permanganate. The conversion of tertiary pentyl chloride into ethyl dimethyl acetic acid also involves an increase in the carbon chain. This can be achieved by first treating the tertiary pentyl chloride with magnesium to yield the corresponding Grignard reagent. The Grignard reagent, on reaction with carbon dioxide followed by acid hydrolysis, gives ethyl dimethyl acetic acid. Let us begin with the physical states of carboxylic acids. The first 9 members, that is, C1 to C9 of aliphatic carboxylic acids, are colorless liquids with sharp or disagreeable odors. Higher members are wax-like solids and are almost odorless due to their low volatility. Coming to solubility in water, the first 4 members of carboxylic acids are fairly soluble in water. Due to the ability of the carboxyl group to form hydrogen bonds with water molecules, their solubility decreases with the increase in the length of the carbon chain. Higher carboxylic acids are virtually insoluble in water due to the greater influence of the hydrocarbon part. The simplest aromatic acid, benzoic acid, contains too many carbon atoms to show any appreciable solubility in water. Carboxylic acids are soluble in less polar solvents like ether, alcohol, and benzene. Let's now discuss the boiling points of carboxylic acids. The boiling points of carboxylic acids are higher than that of aldehydes, ketones, and alcohols of comparable molecular weights. For example, although acetic acid and N-propyl alcohol have the same molecular weight, acetic acid has a boiling point of 118 degrees centigrade, while N-propyl alcohol has a boiling point of 97 degrees centigrade. This is due to the extensive association of carboxylic acid molecules through intermolecular hydrogen bonding. The hydrogen bonds are not broken completely even in the vapor phase. That is why most carboxylic acid exist as dimers in the vapor phase or in aprotic solvents. Let us now look at the acidity of carboxylic acids. The most characteristic property of carboxylic acids is the one that gives them their name, acidity. Just like alcohols, carboxylic acids react with electropositive metals like sodium and liberate hydrogen gas. Unlike phenols, carboxylic acids react even with weaker bases, such as carbonates and bicarbonates, to form the corresponding salts with the evolution of carbon dioxide. The reaction of carboxylic acids with weak bases clearly proves that they are tremendously more acidic than the very weak organic acids, alcohols and acetylene. Hence, the reaction of carboxylic acids with carbonates and bicarbonates is used to detect the presence of the carboxyl group in an organic compound. Carboxylic acids are much stronger acids than water. In an aqueous solution, a carboxylic acid exists in equilibrium with the carboxylate anion and the hydronium ion, as shown in the equation here. As for any equilibrium, the concentrations of the components are related by the expression Keq is equal to the product of the concentrations of RCOO- and H3O+, divided by the product of the concentrations of H2O and RCOOH. Since the concentration of water remains almost constant, we can combine it with Keq to obtain the expression Ka is equal to Keq multiplied by the concentration of H2O is equal to the product of the concentrations of RCOO- and H3O+, divided by the concentration of RCOOH. Here, Keq is the equilibrium constant, and Ka, which is equal to Keq multiplied by the concentration of H2O, is called the acid dissociation constant. Every carboxylic acid has its characteristic Ka, which indicates how strong an acid is. The larger the value of Ka, the greater is the extent of ionization, and therefore, the stronger is the acid. For example, among the unsubstituted monocarboxylic acids, formic acid with the highest value of Ka is the strongest. The values of Ka are usually very small. Hence, for convenience, they are often quoted in logarithmic form as pKa is equal to negative log Ka. Most pKa values fall within the range of 1 to 14. The smaller the pKa, the stronger is the acid. For example, among trifluoroacetic acid with a pKa value of 0.23, benzoic acid with a pKa value of 4.19, and acetic acid with a pKa value of 4.76. Trifluoroacetic acid with the lowest pKa value is the strongest organic acid. Stronger acids have pKa values less than 1. For example, trifluoroacetic acid with a pKa value of 0.23 and trichloroacetic acid with a pKa value of 0.65 are strong acids. Acids with pKa values between 1 and 5 are considered moderately strong. For example, fluoroacetic acid with a pKa value of 2.66, chloroacetic acid with a pKa value of 2.86, and nitroacetic acid with pKa value of 1.68 are moderately acidic acids. Weak acids have pKa values between 5 and 15. For example, phenol with a pKa value of 9.95, orthocresol and with a pKa value of 10.28 are weak acids. Extremely weak acids have pKa values greater than 15. For example, ethanol with a pKa value of 16.0 and acetylene with a pKa value of 23.0 are extremely weak acids. Carboxylic acids are acidic and readily lose a proton because the carboxylate ion formed by ionization or reaction with a base is stabilized by resonance. According to the resonance theory, the carboxylate ion is a hybrid of two structures, which, being of equal stability, contribute equally. The negative charge is evenly distributed over the two oxygen atoms. Let's now compare the acidity of carboxylic acids with the acidity of phenol. When you compare the resonance structures of the carboxylate ion and the phenoxide ion, you can clearly see that the carboxylate ion is stabilized by two equivalent resonance structures in which the negative charge is on the more electronegative oxygen atom. The phenoxide ion, on the other hand, has non-equivalent resonance structures in which the negative charge is on the less electronegative carbon atom. Hence, resonance is more important in the carboxylate ion than in the phenoxide ion. Furthermore, the carboxylate ion is more resonance stabilized than is the phenoxide ion. This is because a negative charge is more effectively dispersed over two electronegative oxygen atoms in carboxylate ions, less so over one oxygen atom, and the less electronegative carbon atoms is phenoxide. Thus, carboxylic acids are more acidic than phenols. Let us now examine the effect of substituents on the acidity of carboxylic acids. Electron withdrawing groups increase the acidity of carboxylic acids by stabilizing the anion through the dispersal of the negative charge on the carboxylate ion by the inductive or resonance effects. For example, chloroacetic acid with the electron withdrawing chlorine group is 100 times as strong as acetic acid. The acidity of carboxylic acids increases with an increase in the number of electron withdrawing groups. For example, trichloroacetic acid with 3 electron withdrawing groups is more acidic than dichloroacetic acid with 2 electron withdrawing groups, which in turn is more acidic than monochloroacetic acid with 1 electron withdrawing group. The strength of the electron withdrawing substituent determines the magnitude of the effect on acidity. For example, fluoroacetic acid is stronger than chloroacetic acid, which in turn is stronger than bromo and iodoacetic acid. This is in accordance with the decrease in the electronegativities of halogen atoms. The nearer the electron withdrawing group, the greater is the acidity of carboxylic acid. For example, among the halo-substituted acids shown here, alpha-chlorobutyric acid with the chlorine atom on the alpha carbon is more acidic than beta, which in turn is more acidic than gamma-chlorobutyric acid. The increasing order of acidity of some of the electron withdrawing groups is as shown here. Note that in the case of carboxylic acids, in which the phenyl or vinyl group is directly attached to the carboxyl group, there is an increase in the acidity of carboxylic acid instead of the decrease expected due to the resonance. This is because of the fact that the carboxyl group is attached to a more electronegative sp2 hybridized carbon. Electron-donating groups, on the other hand, decrease the acidity by destabilizing the anion by intensifying the negative charge. Thus, among the unsubstituted aliphatic monocarboxylic acids, formic acid with no alkyl group is about 10 times stronger than acetic acid, which in turn is stronger than propionic acid, and so on. In the aromatic carboxylic acids too, electron withdrawing groups increase the acidity, while electron donating groups decrease it. For example, para-nitrobenzoic acid with an electron withdrawing group is more acidic than benzoic acid, which in turn is more acidic than para-methoxybenzoic acid with an electron donating group. The chemical properties of carboxylic acids can be conveniently studied under 5 headings. Reactions involving the hydrogen atom of the COOH group. Reactions involving the OH part of the COOH group. Reactions involving the COOH group as a whole. Reactions involving the alkyl group of the acid. Reactions involving the aryl group in aromatic acids. Let us examine the reactions involving the hydrogen atom of the COOH group first. You already know that monocarboxylic acids evolve hydrogen with strongly electropositive metals such as sodium, potassium and calcium, and forms salts with alkalis. This reaction essentially involves the hydrogen atom of the COOH group. The reaction of formic acid with sodium metal and sodium hydroxide is shown here. Note that although the salt, sodium formate, is formed in both the reactions, hydrogen gas is evolved only in the reaction with sodium. Monocarboxylic acids, being stronger than phenols, react with weaker bases such as carbonates and bicarbonates to form the corresponding salts with the evolution of carbon dioxide. This reaction is used to detect the presence of a carboxyl group in an organic compound. For example, in the two test tubes shown here, test tube A contains acetic acid and test tube B contains phenol. When sodium bicarbonate is added to both the test tubes, you can see that effervescence is observed only in test tube A and not in test tube B. The reaction of acetic acid with sodium bicarbonate is shown here. Thus, this reaction can be used as an identification test for the carboxyl group. Now let's examine the reactions involving the hydroxyl group. The hydroxyl group in carboxylic acids behaves like alcohols and can be easily replaced by groups such as OCOR, OR, NH2 or Cl to form anhydrides, esters, amides and acid chlorides respectively. Let's look at each of these reactions in detail. On being heated with a dehydrating agent such as phosphorus pentoxide or with mineral acids such as sulfuric acid, carboxylic acids give the corresponding anhydride. For example, acetic acid, on heating with phosphorus pentoxide, loses a water molecule to form acetic anhydride. Carboxylic acids react with alcohols in the presence of a mineral acid catalyst, such as concentrated sulfuric acid or dry hydrochloric acid gas, to form esters. Reaction is reversible in nature and is known as esterification. For example, acetic acid reacts with ethyl alcohol in the presence of concentrated sulfuric acid to form ethyl acetate. The esterification of carboxylic acids with alcohols is a nucleophilic acyl substitution reaction. The steps involved in the mechanism are: the first step is the protonation of the carbonyl group. In the presence of mineral acids, the carbonyl group of the carboxylic acid accepts a proton to form a protonated carboxylic acid, as shown here. The second step is the nucleophilic attack by the alcohol molecule. Due to the protonation, the carbonyl carbon becomes more electrophilic and is therefore attacked easily by the electron-rich oxygen atom of the alcohol molecule to form a tetrahedral intermediate. The third step is the loss of the water molecule. Proton transfer in the tetrahedral intermediate converts the hydroxyl group into an H2O plus group, which, being a better leaving group, is lost as a water molecule. The result of this step is a protonated ester. The last step is the loss of the proton. The protonated ester thus formed finally loses a proton to give the ester. The OH group of carboxylic acids is replaced by a chlorine atom on being treated with phosphorus halides or thionyl chloride to form acid chlorides. The reactions of acetic acid with phosphorus trichloride, phosphorus pentachloride or thionyl chloride are shown here. Note that although acetyl chloride is the main product in all the three reactions, the byproducts vary. Thionyl chloride is preferred because both the byproducts, sulfur dioxide and hydrogen chloride, being gases, escape the reaction mixture, making the purification of the products easier. Carboxylic acids, when treated with ammonia, form ammonium salts, which upon heating lose the water molecule and forms amides. For example, acetic acid reacts with ammonia to form ammonium acetate. On being heated, this ammonium acetate loses a water molecule to form acetamide. Similarly, a dicarboxylic acid such as phthalic acid forms ammonium phthalate on reacting with ammonia. On heating, ammonia phthalate loses two water molecules to form phthalimide. When this phthalimide is heated further, it loses an ammonia molecule to give phthalimide as the final product. Let's look at the reactions involving the COOH group as a whole. The first one is the reduction of the carboxyl group. Carboxylic acids, on reduction with lithium aluminium hydride or diborane, gives primary alcohols. For example, acetic acid, on reduction with lithium aluminium hydride, gives ethyl alcohol. The second one is the decarboxylation reaction. Sodium salts of carboxylic acids, when heated with soda lime, loses carbon dioxide to form hydrocarbons. This reaction is known as decarboxylation. For example, sodium acetate, when heated with soda lime, gives methane. Cole's electrolysis of sodium or potassium salt of carboxylic acids give hydrocarbons with twice the number of carbon atoms present in the alkyl group of the acid. For example, the electrolysis of a concentrated aqueous solution of sodium acetate gives ethane at the anode. The other set of reactions are the reactions of the alkyl group. Carboxylic acids with an alpha hydrogen react with chlorine or bromine in the presence of a small amount of red phosphorus to give alpha halocarboxylic acids. This reaction is known as 𝙎𝙃𝙊𝙍 reaction. For example, propionic acid, on reaction with chlorine in the presence of red phosphorus, gives alpha-chloropropionic acid. Finally, the reactions involving the aryl group in aromatic carboxylic acids. Aromatic carboxylic acids undergo the usual electrophilic substitution reactions of the benzene ring, such as nitration and sulfonation. The COOH group, being a meta-directing group, directs the incoming electrophile to the meta position. Furthermore, as it is a deactivating group, the reactions occur only under drastic conditions. For example, benzoic acid, on heating with a mixture of concentrated nitric acid and concentrated sulfuric acid, gives meta-nitrobenzene. It is important to note that carboxylic acids do not undergo the Friedel-Crafts reaction because the carboxyl group is deactivating and the catalyst, aluminium chloride, which is a Lewis acid, gets bonded to the carboxyl group strongly. Let's see the important uses of carboxylic acids. Methanoic acid is used as a coagulating agent for latex in the rubber industry. It is used as an acid bath in the textile, dyeing, and electroplating industries. It is used for the dehydration of hides in the leather industry. Ethanoic acid is used as a solvent and as vinegar in the food industry. It is also used in the manufacture of plastics and rayon. Hexane 1,6-dioic acid or adipic acid is used in the manufacture of nylon 66. Esters of benzoic acid are used in perfumery. Sodium benzoate is used as a food preservative for fruit jams and juices in the food industry. Higher fatty acids are used for the manufacture of soaps and detergents.